ABES Engineering College, and I'm going to give a small presentation on optical fiber and its applications, and what are the problems in today's scenario, what are the problems going on for GATE and other competitive exams. So the outline of presentation is optical fiber. What is optical fiber? Its construction, working, basic structure includes construction and working part. Then total internal reflection, it comes under the principal part. Basically, what is the principle on which this optical fiber works? So it works on the principle of TIR, that comes under ray optics. Then two important parameters I am going to explain. One is numerical aperture and other is acceptance angle. These two again are very important regarding their formula, regarding their explanation for any of the competitive exams. Then problems and solutions. What is optical fiber? An optical fiber, it is flexible, transparent fiber made up of glass. It can be made up of glass, it can be made up of silica, and it is slightly thicker than our hairs. It functions as a waveguide, means it is a very good way of communication. It helps for data transmission from one end of the optical fiber to the other end of the optical fiber. Then it is widely used for fiber optics communication, which permits data transmission over long distances. So why long distances? Because in optical fiber, everything works with the speed of light. And as we all know that nothing is greater than the speed of light. So the speed of communication is very fast. It works on the basis of TIR. I am going to explain it more in my further slides. So the basic structure, we can understand it like we have a pen. The pen is having two layers. One is the innermost layer, which we call as a riffle, and the other one is the outer layer, which basically protects the pen, and it also helps us for holding it. Similarly, we have an optical fiber, and this optical fiber has three layers. The innermost layer is the core, which is having the refractive index N1. Then cladding is the second layer, which is having the refractive index N2, and the outermost layer is the buffer shed, and it is also called as mechanical shed. So what are the roles of these three layers? Core and cladding. Inside the core, the ray enters, whatever data we have to communicate. So the light ray enters inside it, and the light ray propagates inside it by the principle of total internal reflection. The very important point inside this is that N1 will always be greater than N2. Only in that case TIR will work, and only in that case the data will be, we can able to communicate the data. Then buffer shed, it is the outermost shed. There is no role of refractive index in this case. It protects the complete optical fiber from any kind of damage, any kind of outer damage due to environmental condition, absorption, scattering, and many more other effects. So it basically protects the optical fiber from any kind of physical damage. So very important point in this case is that N1 should be greater than N2. Then and only then the optical fiber will work. Coming to the next slide, total internal reflection. It is a part of the ray optics, and the optical fiber, it works on this principle. Now what is this principle? We can say that N1 and N2 are different refractive indices. N1 is the highest refractive index and N2 is comparatively less as compared to N1. As I have already told that in case of optical fiber, N1 will be greater than N2. Core refractive index will be greater than cladding refractive index. So we all know whenever a light ray moves from higher refractive index to lower refractive index, N1 to N2, the light ray will bend away from the normal like this. Now, if we increase this angle, and this angle is increased at some particular angle, critical angle we will say. If I say that it will be theta I greater than In this case, it will be theta 1 equals to critical angle. In this case, theta 1 was less than some particular critical angle. So light was deviating away from the normal. Now we have increased this angle. Now this angle is equal to some particular critical angle. This means that the ray will again deviate more. A stage will come when this ray will go along the axis of the optical fiber. So this is the starting of TIR. This is a special condition, critical condition, when your input angle or incidence angle is equal to the critical angle. The third case is when we increase this angle greater than the critical angle. Means your theta 1 or phi 1, it's phi 1 over here. So it will be greater than some particular critical angle. In this case, now the ray will deviate from its axis also. It will come down. Now it will follow the path of TIR, the path of communication, the path which is followed in the optical fiber. So this is a part of ray optics which is followed in the optical fiber. So coming to the next slide. Now coming to two important parameters, which is numerical aperture and acceptance angle. What are these two parameters? See, we have an optical fiber. It's not necessary whatever the ray we are incident inside this optical fiber, it will follow TIR. There must be some particular angle. There must be some acceptance angle. There must be some angle which this fiber is accepting in such a way that TIR should be there. So that is the acceptance angle. So this is the acceptance angle in which when a ray enters inside the optical fiber, it must follow the principle of TIR, total internal reflection, like this. So in order to derive this, we are going to start from particular Snell's law in the next few slides. Then what is numerical aperture? If we have some particular angle which we are saying acceptance angle, the sign of this angle, sine theta max, sine theta I, this will be a numerical aperture, and physically we can understand it like this, that it tells the light gathering capacity of the optical fiber. Acceptance angle, we can define it as the maximum possible angle which the fiber can have so that TIR, total internal reflection, must take place. In order to derive this, we are going to start with the Snell's law. Now what is the Snell's law and how many times we are going to apply this Snell's law? Snell's law is applied 2 times over here. We can see this is an optical fiber. The outer medium, this part is the core and the boundary part is the cladding. The innermost part is the core part which is having the refractive index of N1. Then cladding is having the refractive index of N2, and we are also taking the outer medium which is generally the air medium, but still we are taking outer medium refractive index as N0, which will be 1 because the outer medium is air. First we are going to apply the Snell's law at outer medium and core interface. Second time we are going to apply the Snell's law at core and cladding interface, in order to find out what is the numerical aperture and what is the acceptance angle. So we can see when we are applying Snell's law at outer medium and core interface, then it will be N0 sine theta I is equals to N1 sine theta R. Refractive index of the outer medium multiplied by sine of input angle related to it, and the other side of the boundary, the refractive index of core and the angle which is associated with it. So due to which we are getting theta I, input angle, that is N1 upon N0 sine theta R. It will be as it is. Now we have to find this theta R in terms of the critical angle, that is phi. So what we'll do, we'll make a right angle triangle, we'll complete this geometry, and if we complete this geometry, then due to some particular theorem, we can easily find what is this theta R in terms of phi. Now what is this theorem? This theorem is your sum of interior angle of a triangle is 180 degree. We can see if we are completing this geometry, it is theta R plus phi plus 90 equals to 180. Right? So theta R will be 90 minus phi. If we are going to use this in equation number 1, then sine theta R, sine 90 minus phi will be cos phi. So that will be what I have written in this equation number 3. The input angle, the input incidence angle will be N1 upon N0 cos phi. Alright. Applying condition. What is this condition? This is a boundary condition, starting condition of TIR. As I already explained, that if this phi will be equals to some particular critical angle. In that case, this ray will go as it is. This ray will go along the axis of the optical fiber. So this is a critical boundary condition which we are going to apply. So on applying this condition, that theta equals to theta max, your phi will be equals to phi c. In that case, your theta max, we are going to just change this equation number 3 and we are going to get theta max as n1 upon n0 cos phi c. So this is our equation number 4 and this is very important equation regarding our numerical aperture part. We can easily find out cos phi in terms of equation number 3. Instead of cos phi, we can write it down as under root of 1 minus sine square phi c. We are just putting the values. What we are doing? Theta I, we have written it theta max. Then cos phi, I have changed it to cos phi c by applying these conditions. So theta max will be n1 upon n0. Instead of cos phi c, it will be under root of 1 minus sine square phi c. So this is the role of first Snell's law. Now we are going to apply the Snell's law second time, where at core clad interface. So core refractive index, its angle associated to it, then cladding refractive index and its angle associated to it. So we can see n1 sin phi c equals to n2 sin 90. I am repeating it. Core refractive index, angle associated with it, then cladding refractive index and angles associated with it is already 90 degree because the ray is now going along the axis. So if we are going to simplify this, we are going to get a very good equation. It is very important for competitive exam also. That is the formula for critical angle, that is phi c. Sin phi c equals to n2 by n1. If we are going to solve it, we are going to get sin phi c n2 by n1. And if we are going to use this equation 5 in equation number 4. Here we are going to use this formula. So we are going to get the formula for numerical aperture, that is theta max. This is basically the acceptance angle, the maximum possible angle, n1 upon n0 under root of 1 minus n2 by n1 whole square. So in this case, n0 will be 1. As I already explained, we are taking the outer medium and as air, and the air refractive index is 1. So numerical aperture formula will be simple, sine inverse of under root of n1 square minus n2 square. So we are having 3 formulas here. One is the critical angle formula, this one. The other one is your acceptance angle formula, this one. Theta max is the maximum possible angle, and the third important formula, important parameter is your numerical aperture, which is sine inverse of your acceptance angle under root of n1 square minus n2 square. Right? So going to the next slide. These are few problems which generally comes in any of the competitive exams, and they are very easy, formula based. So we can have a look at 1 or 2 problems. An optical fiber has a core refractive index 1.480 and cladding refractive index is also given. See, sometimes it happens in most of the exams, they don't give that this is a core refractive index and this is a cladding refractive index. You have to figure it out, what is the core one and what is the cladding one. So it's very easy to figure it out. We all have to remember that n1 will be greater than n2. Core refractive index will be greater than cladding refractive index. So without any if and but, we can easily say that n1 will be 1.480, n2 will be 1.478. We have to find numerical aperture. We are going to apply the formula under root of n1 square minus n2 square. We are going to solve it and we are going to get the answer around this one, 0.077. In the next question, we can see we have to find the acceptance angle related to this problem itself. So what we have to do again and again, we don't have to find under root of n1 square minus n2 square. It's simple. Acceptance angle means sine inverse of numerical aperture. It may be, you can write this as sine inverse of under root of n1 square minus n2 square. This we have already calculated. So it will come around sine inverse of 0.077, which will come around 4.41 degree. So third answer is correct. Coming to the next problem. The last question for today. An optical fiber has a refractive index of 1.47 and 1.45. Again, N1 and N2 is not given to you, but we can easily figure out that N1 will be 1.47 core refractive index and cladding refractive index is 1.45, and we have to find the critical angle phi. Phi critical angle will be sine inverse of what? If we are talking about core clad interface, then in that case it will be N2 by N1. Cladding refractive index upon core refractive index. This question may change. We can get what is the critical angle at outer medium and core interface. In that case, these refractive indices will change. So if we are going to solve it, it will come around sine inverse of N2 means 1.45 and N1 is 1.47. So it will come around 80 degree, means third part is correct. So you all practice these three important parameters: numerical problems, questions, then optical fiber, its benefits, why is it important, then what are the construction part involved in optical fiber, and then you may go in you may have lot of number of questions regarding these three important formulas. So thank you so much for today. Have a nice day.